video will cover logarithms, including logarithmic algebra and logarithmic equations. Logarithms do not form a big part of the syllabus, and in many cases, this section is not taught very well because of that fact. However, they come in handy when dealing with logarithmic graphs and solving those graphs and getting inverses, and it is good to know all of the algebra and the laws when it comes to logarithmic equations. So firstly, we use logs to calculate the value of an exponent. If we look over here, we have log base A 1 equals x. Now if we look to the right over here, the log form is you take the log of a base being the base. So if we were to write this in exponential form, it would be a, because a is our base, to the x, because x is our exponent, equals b being the constant. So when we write it in logarithmic form, we go log base, a is now our base, b is our constant or our number that our exponent and our base are equal to, equals our exponent. And in this way, it enables us to solve for x being our exponent. So as you can see here, a is now our base, 1 is our constant, which is what a to the x would have been equal to, and we're now solving for x, which is shown here. Our base is a, our exponent is x, and our constant is 1. We can see that x is then 0 because any constant to an exponent to equal 1, your exponent would have to be 0. Now when dealing with logs, we need to know that in this format, your base, this number over here, has to be greater than 0, it cannot be negative, and n in this form cannot be 1. Simply because if it was 1, your base would be 1, and 1 to any exponent will be 1. So it would kind of make this redundant to even do the calculation. So we just say that n must be greater than 0 because it cannot be negative, and n cannot be 1. Further, m, which is your constant value that your exponent and your base are equal to, must be greater than 0. That is simply because a constant to an exponent, a positive exponent, cannot be negative. So m has to be positive. Now when we look at logarithmic algebra, there are a number of rules that we need to know. If we have two logs, so log x plus log y, there is a rule that we can use to form this into one logarithm, and that is log x times y. We simply take this constant and this constant, multiply them together, and we get one log. In a similar way, if you have log x minus log y, it is then log of x over y. We now divide this constant by this constant, and we simply get one logarithm. When you are given a logarithm in this format over here, m being a constant, log base a x, you can change that into the form log base a x to the power of m. In the same way, you can work backwards and move the m down. This is often useful when solving equations and dealing with logarithms in algebra, because you're often able to bring your exponent down and then work with it from there. It's also good to note that if you're given a logarithm where a base is not stated, so it's not log base 2 8, you're simply given log 10 as shown here, it is implied that your base is 10. Here are some extra laws that may be useful to know, however they do not form part of the syllabus and they are not essential. If you have log base a m and you want to change the base, so you want to change this a to a p, this is known as the change of base law, and it follows like this. So if you have log base a m and you want to change to a base of p, you simply go log p of m, being your constant over here, divided by the log base p a being your base. So this is a rule that you can follow if you wish to change your bases ever. Just know that it's log of your new base of your constant over log new base of the base that you had. And then this is a second extra law which may come in handy. However, I've never seen it in the syllabus, and it will most probably not be required of you to use this law. However, I will go through it just in case some of you may want to use it. If you have a to the exponent of log base ax equals x, you can then say that log of 1 over a x, taking that, equals log base a 1 over x, simply by inverting, which we can then say, because this is x to the negative 1, we can take that negative 1 down from this law over here, where negative 1 is our m, we take m to the front, negative 1, and therefore negative 1 log ax. This law, as I said, is more complicated than you should be required in matric, but it is useful to know in cases where you may get a more complicated logarithmic function. Then we move on to logarithmic equations, which are very simple and no one should have a real problem with them. Simply, when you're solving a logarithmic equation, you need to get single logs with the same base on either side. So to do this, normally you will have to use your logarithmic algebraic laws, and once you've got it in a form where you have the same base with a constant and a same base with a different constant, then you can say that this constant equals this constant and solve from there. So if we look at an example such as this one, we have the log of x plus 2 squared equals 2. Now we know that the log of x plus 2 squared has a base of 10 because no base is shown, so therefore it is implied that the base is 10. Now 2 is not in logarithmic form. However, log base 10 is 1. And in many cases, this is something to look out for. If you are given a constant, you are often required to add in a log that is equal to 1 in order to get a logarithm on both sides. So in this case, we now leave the left-hand side because we've got a base of 10. And on the right-hand side, we've also got a base of 10. However, this 2 is a problem. We need one logarithm, not a logarithm with a constant. So we know from our law where this is a constant that we can raise it to the exponent. We do that and we get the log of 10 squared, which is 100. Therefore, we've got the log of 100. Now we have a log here with the base 10 and a log here with the base 10. We can therefore say that this constant over here equals this constant over here, which we've done here. X plus 2 squared equals 100. And we simply solve that like we would any other equation. Here we have a slightly more complicated one. So we have log base 2x plus 1 equals 2 over log base 2x. Now, in cases like this, it's often easier to simply use substitution. So we do that. As shown here, we substitute log base 2x with k. Therefore, it's k plus 1 equals 2 over k. Simply multiply that out by your lowest common denominator, and you get k squared plus k equals 2. We solve this like we would any other quadratic, and we come out that k equals negative 2 or k equals 1. Now that we've got the values for k, we have to sub back in our log base 2x. So we do this here. Remember that you have two cases because k came out with two values. Log base 2x equals negative 2. We simply take our base, so our base is 2. Our exponent is negative 2, so 2 to the negative 2 equals x. Therefore, x is 1 over 4. In the same way, we go log base 2x equals 1 because 1 was our other solution. Therefore, our base is 2 to the exponent of 1 equals x. Therefore, x equals 2.